Okay, for this last type of line integral, I want to start with the motivation of computing work done by a force field. So from chapter 12, we can recall that when you have a force being applied to move an object across a distance, but the force is not directed directly in the direction of motion. So let's use D for the displacement vector, connecting the 2 points that the object is moving and the force is going in some other direction. Then we remember that the work is computed through a dot product. Okay, now let's consider a more complicated situation. I want to say that the force that's being applied to the object varies as the object moves around in space. So at every single point in space, I have a different force vector. Well, that's called a force field. If you attach to every point in space a particular force vector, then you're building a field of force vectors, a force field. So I want to imagine the computation of work that force field applies in moving an object from one point to another across a parameterized curve. So let me draw a curve like this. Imagine it in space. Let's say it's parameterized by the vector function r of t. And this could be 2D or 3D, doesn't matter. And then I have forces acting on every point in space, let's say, and they vary as you move around in space. So I'm just drawing a bunch of sort of random vectors here. Okay, let's say that this is the starting point. Let's say at time A, and let's say this is the ending point. And what I want to compute is the work done by this force field in moving an object along the curve C from the beginning to the end. All right, well, it's going to be an integral that computes the work done precisely. So as usual, when creating integral formulas, what I do is I take this large problem and I chop it up into a million little problems. So I know how to compute the force done in moving an object from point A to point B along a straight displacement given a fixed force vector. That's just a dot product. So I'm going to take this long curved motion with the varying vectors and split it up into a bunch of these problems. Okay, so what I'll do is I'll partition the time interval, A to B, up into a million pieces, in effect chopping up the curve into a million pieces. Each of those isn't a straight line, but if our curve is nice enough, they'll be pretty close to straight lines. And let me focus my attention on computing the work done and just moving the particle across one of these small segments. So let's fix our attention from here over here. Well, an approximation for the displacement of the particle from here to there, I could use a tangent vector. So the tangent vector is close to the curve. And let's see here, how long is that tangent vector? Well, a unit tangent is length 1, and then the length of the curve there is like a little delta s, change in arc length. And let's see here, what is the work done by the force field in moving a particle along this displacement vector? Well, let's find the force field's vector attached at that point. Let's say it's right there. And the approximate work done in moving a particle from here to there would be this tangent vector dotted with that force vector. So that's our estimation of work across that one interval. So skipping the gory details of the precise Riemann sum to build the integral that computes this work, I see right here the fundamental unit of computation, right? I compute this amount for every single one of the segments, I sum it up, and then I let the number of pieces go to infinity, and that creates my integral. So it may be no surprise that this exact expression appears in the integrand of our line integral. So what we have here should look something like this. We're running along the curve, so we're taking a line integral along the curve, and we're computing f dot t, and then in the integral, the delta s becomes ds. Okay, again, so if you're interested in the gory details, read the chapter. It's got all of the proper Riemann sum construction. But this is basically our new integral. Now, we're going to have a few different notations for this integral. So you can see right here the computation of work, like I said. This now becomes a new type of integral, the line integral of a vector field along a curve. And this is how you're going to compute it. The R of t function parameterizes C, the time variable goes from A to B, and the computation of f dot t, which I'll show in a second, reduces down to this right here. Okay, and this last bit on the far right, this is our notation. This is like the name of the line integral. So this just says the line integral of the vector field f across C. This is how to compute it via parameterization, and this is what it is from the picture of computation of work. Okay, so let me show you how this integrand arises from writing out f dot t ds via parameterization. Well, the force vector at any particular point along the curve is found by plugging in the point along the curve, r of t, into the vector field. So that's where the r of t appears there. Now, the unit tangent vector we know to be the tangent vector, r prime of t, divided by its magnitude. And finally, ds, we recall from long ago, is the speed dt. So ds is magnitude r prime of t dt. So these two cancel, and that's why this integrand is computed as we have in the middle here. Okay, so let's practice using a parameterization to compute a line integral of a vector field. So let's find the work done by this force field. So this is a two-dimensional problem. On a particle moving along this parabola from 1, 0 to 2, 1. So this is the description of the curve C, and then this is a description of the force acting on the particle at any time. So it looks like x is a function of y. I'm going to go ahead and use y as the parameter then. There's a parameterization of the curve C, and now I'm ready to set up my line integral of the vector field. Okay, so here is the parameterization and the derivative, r prime. And then I want to carefully put in the components of the parameterization into the vector field. So I'm computing right here what the force vector is at any point along the parameterized curve. So look up at the force field to its definition to get that force field vector. And now I take a dot product, and I'm left with the Calc 1 integral to integrate. All right, one more thing that I wanted to say about these line integrals of vector fields. If you notice, right at this stage right here, what I had was two line integrals with respect to x and with respect to y. Why is that? Well, this right here is dx, well, 2t dt is, and this right here is dy, 1 times dt is. And so at this stage in computation, what I have is a function, dx, and then another function, well, this I guess, dy. And that's sort of true in general. If you compute this dot product out, what you're going to end up with is something that looks like this. So if the force field function has component functions p and q, after you've performed your dot product, this is what you're looking at. Well, this is two line integrals of the following form. Okay, and typically we, if we're looking at a particular line integral as the sum of these type of line integrals, we may sort of abuse notation and write it like this and use one integral sign for both. So my point here is that the line integrals of vector fields over curves are the sum of line integrals of multivariate functions with respect to the variables. So the same exact thing could be said if I was computing the line integral of a vector field across a three-dimensional curve.